Welcome back, everyone. In this series of lectures, we're going to now learn how to deal with color data, and we'll do this with the CIFAR10 dataset. So in part one, we'll focus on the actual data itself, as well as creating our model. And the CIFAR10 dataset are slightly larger images than what we just dealt with. They're 32 by 32 images of 10 different objects. So the different types of objects available are airplanes, cards, birds, cats, deers, dogs, etc. And the main thing to note is these are color images. Keep in mind, 32 by 32 is still quite small, but you'll be able to see some level of detail that a human can discern what's actually in the image. So in this series of lectures, we're actually going to be reusing a lot of the previous convolutional neural network code. So really what we're going to focus on is the additions necessary due to the introduction of the three color channels, that is the red, green, and blue color channels. So let's head to a notebook and get started, and we'll be copying and pasting quite a bit of the code because about 90% of the code is the exact same as the previous series. It's just a couple of additions to deal with the three color channels. Let's head to a notebook to get started. Okay, here I am at a notebook. I've already imported the basics. Let's load up our data set. This one is also built into Keras for learning purposes. We will say from tensorflow.keras.datasets import CIFAR10. And then we'll load it really similar to the way we did last time. It's actually already split for us. When we run load data, we load up the training pairs and the test pairs. And then we set that equal to CIFAR10 load data. Go ahead and run that, and it will load up the data for you. And let's take a look now at the shape of our data. So notice now the shape has an extra dimension to it because there's three color channels. So there's 50,000 images. They're 32 by 32, and there's three color channels, a red, green, and blue color channel. So let's take a look at just a single image, xtrain 0, and it's this array right here. Let's go ahead and check out the shape of it. It's 32 by 32 by 3. Let's say plt.imshow and show you what this actual image looks like. And hopefully you can kind of blur your vision a little bit and see that this is an image of a frog. And you can pass in random numbers here within the 50,000 points to see different images. So here we can see this is an image of a horse. These are very small images. They're only 32 by 32, but there's enough information here for a human to detect what it's looking at. Some of these, keep in mind, are a little less clear. So I'm just kind of randomly choosing here. This one may be a little less clear. To me, it looks like a deer, and we can check that against the labels. I believe this is a deer, but you can see that because the images are so small, some of these are kind of bound to be misclassified. So we won't get as good performance as we did on the MNIST dataset. Okay, so just as before, we need to perform pre-processing. Right now, if we take a look at one of these images and ask for the max value, they go from 0 to 255 for each of the color channels. So we'll do the same thing as before. We'll simply say xtrain is equal to xtrain divided by 255. And keep in mind, you should only be running these commands one time. Otherwise, you'll be dividing by 255 twice. So keep that in mind. Then we'll say xtest divided by 255. Go ahead and run that. And if we take a look at the size or shape of xtest, there's 10,000 images in the test set. Okay. Also, just like before, if we take a look at our Y training data, you'll see that the labels themselves are just as we did last time. They're labeled by an integer. So what we actually need is not have these be read in as continuous values, but as categorical values. And just as before, we can convert these by saying tensorflow.keras.utils import to categorical, and then we'll transform these to be categorical. So we'll say that my Y categorical for my training set is equal to 2 categorical on Y train, and we can specify that there's 10 classes here. And we'll do the exact same thing for our test set. 2 categorical on Y test 10. So far, as far as reshaping anything, nothing has changed from what we did with the black and white images. The scaling still works exactly the same because with NumPy, luckily, this division by 255 happens across all three dimensions on the color channels. So it's scaled across all of those, so we don't need to worry about that. And the labels themselves, same deal as last time, we convert them to categories. And as a quick note, a common question is, well, what do these numbers actually represent? Because if we take a look at, for example, y-test of 0, recall that number 3, if we take a look at, actually, let's take a look at train. So y-train of 0, it says the label is 6. Well, let's say plt imshow on x-train of 0, and we see the result. That was a frog. So how do we know that 6 actually connects to frog? If you just Google search CIFAR10 label names, it will show you just a list, like airplane 0, automobile is 1. So I can see here frog is 6. Or you can go to the official website, CIFAR10 dataset, and it has them organized in that order. So airplane is 0, automobile is 1, etc. So this is the official website. If you just go to CIFAR10 dataset and then just look up the official website on Google, you'll find it. There's also a larger labels. So there's the CIFAR10, but that is much too big of a data set for us to run, and it's the same idea as CIFAR10. Okay, so we'll come back to our notebook. We understand how to work with the data. We understand the labels. Let's go ahead and build out our model. And what I'm going to do is I'll be copying and pasting some of this code from our notebook because it's pretty much the exact same as we did last time. The only thing we need to edit is our input shapes. So let's go ahead and build out our sequential model just as we did before. And let's add in a convolutional layer as well as a pooling layer. I will copy and paste this code from our notebook and then just note the changes. So the main change here is we'll still use the same number of filters, the same kernel size. However, recall that the input shape is defined by our data. So this should be 32 by 32 by 3, which is defined up here when we checked out the actual shape of a single image in Xtest, which was 32 by 32 by 3. Okay. Now, when you're dealing with more complex images, recall now that a single image, if we just take a look, or if we think about the number of pixels or data points really inside of a black and white MNIST image, the total number of values was 28 times 28, which is 784. The total number of values within a color image here is going to be 32 times 32 times 3. As you can see, there's a lot more information within this color image than there was in the previous MNIST dataset. Because of that, it's probably a good idea that as our images get more complex and larger, and also more complexity due to the color, that we add in more convolutional and pooling layers. So we'll go ahead and copy and paste this and add in another convolutional layer as well as another pooling layer. And often, researchers also like to have different amounts of filters in the different number of layers. So you can have expanding number of filters as the convolutional layers go deeper. For our use case, these images are pretty simple, so we'll keep everything the same. Okay, then we'll go ahead and keep it to just 2 convolutional layers followed by 2 pooling layers, and we'll flatten out the images just as we did before. So we flatten out the images, and because of the added complexity of the number of points here, when we're adding in our dense layer, we'll go ahead and add more neurons to it. We'll say 256 neurons with the activation function equal to a rectified linear unit. And then finally, everything else is going to be pretty much the same. We'll say model, go ahead and add dense. The activation function should be equal to softmax because it's a multi-class function. And then we compile the model. We'll say model, compile. The loss should be categorical cross entropy. You can choose whatever optimizer you want. We'll go ahead and just choose the atom optimizer. That should be fine. And if we want to keep track of different metrics beyond just loss, we could say metrics is equal to, and I can pass in that accuracy call. Okay, run that, make sure you have no typos. Looks like that went well. You can order a summary of your model by saying model.summary. Here we can see the different layers. And let's go ahead and add in early stopping. So we'll say from TensorFlow .keras.callbacks, import early stopping just as we did before. We'll create an early stop call. We'll say early stopping. We'll monitor the loss. You could also technically monitor the accuracy if that was your most important metric. And then let's give it a patience of 2. And let's fit this. We'll say model.fit, fit to the training data. Make sure you correctly fit to the categorical versions of the labels. Say epochs. Let's just choose a larger number, probably won't change or train for 15 total, but we have the early stopping to make sure. Make sure you specify your validation data. That's equal to X test and Y categorical test. And then finally add in the callbacks for the early stopping. Fit that. Make sure you see that first output to make sure you're doing this correctly. And that's pretty much it. So you notice on this very first epoch, the accuracy isn't so good. But as we continue training, we should see that accuracy go up. And that's what's kind of nice about adding in accuracy as a metrics call here, because it's pretty hard to interpret the loss beyond just that it should be going down. What's nice is I can really interpret the accuracy very intuitively and can see it go up as the epochs get trained further and further. Okay. The other thing to keep in mind is that default accuracy by random guessing should actually be 10%. So the fact that we're going above 10% is really good, and we're going way beyond that. Because if you were to randomly guess what class an image belonged to, you'd have a 10% chance of getting it right. But here, based on epoch 7, we're already performing at 0.75% accuracy. So we're doing pretty well on this data set. All right, I'll end this lecture here, and coming up next, we'll talk about evaluating the model, and we'll also talk about performing predictions on new data. I'll see you there.